All right, for today's class meeting, we are going to be talking about capacitors and capacitance. And this lecture will be extraordinarily similar to what we did last Thursday with regards to inductors and inductance. The reason for that is that capacitors and inductors are what are called electrical duals. Meaning that they behave using pretty much the exact same relationships, except that we're going to, everywhere that we saw voltage for an inductor, we're going to replace it with current, and everywhere we saw current for an inductor, we're going to replace it with voltage. But before we get into that, let's talk a little bit about what a capacitor is. So the most commonly seen capacitor is the parallel plate capacitor. So imagine that we had a metallic plate. This is going to be our top plate, and we are going to connect an electrode to it. And below this top plate, we have a bottom plate. Like so. We have another electrode down here. And then sandwiched in between these plates, we have what's called a dielectric material or dielectric medium. And the dielectric medium plays a similar role to that of the ferromagnetic core seen in an inductor. What the dielectric medium's role is to enhance and concentrate an electric field that is observed passing between the two plates. So in an inductor, we had magnetic fields being concentrated due to the presence of ferromagnetic cores. In capacitors, we have electric fields being concentrated due to the presence of a dielectric medium. And these are the energy storage elements of our circuits. Okay, so imagine, if you will, that we applied some voltage V of t across the plates of our capacitor. And this voltage is going to be slowly increasing, right? So what we would observe is that positive charge would gradually accumulate on this top plate. So we're going to have some Q plus here, and that will attract the same amount of negative charge onto the bottom plate. Okay. The attraction of charge, so placing it or moving it onto the top plate and the bottom plate, causes what's called a displacement current to flow through our capacitor. Okay, so there is no actual conductive path from the top plate to the bottom plate, but we can still get what behaves like current, charge moving, as we move charge onto the plate and then allow charge to go away from the plates. Okay, so even though there is literally a physical barrier separating charge moving from the top plate to the bottom plate, we still observe current flowing, but it's not typically the same as the traditional current we've been dealing with, although it behaves effectively the same way. Okay. So from this simple look at a capacitor, we can see that there is a relationship between charge, voltage, and capacitance, right? So capacitance, which is measured in farads, where 1 farad F is equal to an amp second per volt, is simply the ratio of charge Q to voltage V. So capacitance can be thought of as a measure of how an element behaves to a varying electric field. If we vary voltage, we get a variable electric field, much like in an inductor. If we vary the current, we get a varying magnetic. For capacitance, I've defined the units in electric fields, and we've tied it back to some quantities that we're familiar with, charge and voltage. So now I want to introduce our mathematical relationships, much like we had for the inductor, right? So I'm going to draw the schematic symbol for a capacitor. Here we go. So this is the schematic symbol for a capacitor. This is a general or generic capacitor. I'm going to choose the positive polarity terminal to be on top and the current flowing into the positive polarity terminal, like so. The symbol is simply 2 parallel plates, okay? You may also see this symbol used for capacitors as well. Technically, this symbol is only appropriate for what are called electrolytic capacitors. Electrolytic or polarized capacitors. This type of capacitor is used a lot in very sensitive electronics. So like if you were to look inside your computers, actually, almost all of the capacitors there would be electrolytic capacitors. You can typically tell an electrolytic capacitor from a parallel plate capacitor because an electrolytic capacitor is usually, not always, usually cylindrical in shape. And the top of the element is going to have a metal plate that has been scored. And so if you ever connect the wrong polarity voltage to an electrolytic capacitor, that the material inside will heat up so rapidly that it will cause the top plate to deform, and that capacitor is no longer functional. Our voltage and current will be of the same polarity and direction respectively, right? So you may see the electrolytic capacitor symbol used in some homework problems and stuff for this class, but there's really, whenever you see that, treat it just the same as if it were a regular capacitor or generic capacitor. We are not doing any labs or anything like that, but all of the labs associated with this class only use non-polarized capacitors because we don't want to spend a whole bunch of money while you guys blow them all up accidentally. Anyway, so for either of these capacitors, the relationship between voltage and current could be expressed as I is equal to C dV by dt. So this is going to be our first equation. The current flowing through a capacitor is equal to the capacitance value multiplied by the derivative of the voltage drop across the capacitor. As a quick aside thing here, for an inductor, we saw the relationship V is equal to L di by dt. The exact same relationship, except that we've replaced our capacitance, excuse me, our inductance with capacitance, and we've swapped voltage and current. All of the relationships for capacitors are going to behave the exact same way. You replace the inductance with capacitance, swap positions with voltage and current, and you're done. Okay, so we're not going to spend a whole heck of a lot of time deriving things because we've really already derived all of the relationships because of the dual nature between capacitors and inductors. So when we were looking at the derivative-based relationship for inductors, we came up with two smaller or two sub-relationships based on this, right? The first of which was in a DC circuit, inductors behave like short circuits. Well, in a DC circuit, capacitors will behave like open circuits. So if the voltage does not change, the current is zero, and the way to force a current to be zero is to replace it with an open circuit, okay? So in any DC circuit, you can simply treat a capacitor as if it were an open circuit, or take the capacitor out and analyze it that way, and you'll be doing everything correctly. Okay? Our other thing that we got from our derivative-based relationship for inductors was that the current flowing through an inductor could not change abruptly. Well, for capacitors, it is the voltage that cannot change abruptly. If the voltage changes instantaneously from one value to another, that means the derivative of that change in voltage is infinity, which would cause an infinitely large current to flow, which would violate the in a capacitor. So now we're going to take this first relationship, our derivative-based relationship, and mathematically manipulate it a bit. In doing so, we will come up with the following relationship. The voltage drop across a capacitor is going to be equal to 1 over C times the integral from negative infinity to t of the current flowing through the capacitor as a function of time. And we can do just what we did with our inductor relationship. We can break this up to show that capacitors also have a little bit of memory, meaning that the present value of the voltage drop across the capacitor depends on past values of the voltage. Right? So this is going to be relationship 2. Okay. So we use relationship 1 when we want the current and we know how the voltage is behaving. We use relationship 2 when we want the voltage and we know how the current is behaving. The power absorbed by a capacitor is the product of voltage and current, which could be rewritten as C V dV by dt. So much like we were able to do inductors, we could express the power purely in terms of the current. For capacitors, we can express the power purely in terms of the voltage. And our energy relationship, W, is going to be 1/2 E V squared, as opposed to 1/2 Li squared for inductors, right? So these are our 4 relationships. So let me put boxes around them that define how capacitors behave in an electrical circuit. So the last thing that I officially want to talk about is how we combine capacitances in a circuit. So let's start with capacitors in series. If I have a part of a circuit that contains multiple capacitors connected in series, like so, there will be a total voltage drop across all of the capacitances, V of t, and because all of the elements are connected in series, they will all share the same current, I of t. I'm going to express the voltage drop across my individual capacitances as V1, V2, all the way out to V sub n, like so. And by applying Kirchhoff's voltage law, I can see that V of t, the total voltage drop, is going to be V1 plus V2 all the way out to V sub n. I can express all of those voltages in terms of my common current, I of t. So I'll have 1 over C1 times the integral from negative infinity to t of I of t prime dt prime plus 1 over C2 times the integral from negative infinity to t I of t prime dt prime all the way out to 1 over C sub n times the integral from negative infinity to t of I of t prime dt prime. And I can lump all those integrals together because they're a common factor, which is going to give me 1 over C1 plus 1 over C2 plus 1 over C3, or excuse me, C sub n times the integral from negative infinity. Fix this. T I of t prime dt prime, or 1 over CEQ times the integral from negative infinity to t of our current. So from this, we can actually see that capacitors in series combine like resistors in parallel. And it shouldn't be particularly difficult to understand then that capacitors in parallel will combine like resistors in series. So on your next exam, you are going to be expected to understand all 4 of these capacitor relationships, as well as all 4 of the inductor relationships that we covered in class last Thursday. Instead of just rote memorization, I would actually encourage you to simply memorize, or learn would be even better, how inductors behave or how capacitors behave, and then just understand that inductors and capacitors behave opposite each other. So if you can learn how one of the elements works, just do the opposite for the other element, and you don't have to do anything else. Okay. So this is where my lecture officially ends, because I've covered everything that I wanted to with regards to capacitors. What I'd like to do now is look at our web work assignment and show you guys a couple of problems that I like. And so by me saying that I like these problems, I am effectively telling you to expect something similar to this on your upcoming exam. Did not want to open Edge. So if I am not mistaken, this is homework set number 12. And let's look through things here. So this first problem here is fairly straightforward. For part A, you're given the voltage, you're asked to find the current. So you simply take the derivative of the voltage. Nothing wild there. Maximum energy stored in the capacitor. That can be a little problematic if you go about it the way that you would think you're supposed to go about it. I would argue that just finding the maximum voltage will allow you to find the maximum energy, more so than squaring this function, multiplying it by c, and then taking the derivative of the function as a lot of work. So, but if you find the maximum value of the voltage, that will be the voltage at which, or you can use that to find the maximum energy stored in the capacitor. It's a little bit easier to do it that way. For part C, you're given the current, you need to find the voltage. So that's the integral based relationship. Part D is the exact same thing, except that you have an initial condition that is no longer 0. Part E, you're asked to find the current if you're given the waveform for the energy. So you could effectively divide by C and take the square root of the energy to give you the voltage, and then take the derivative of the voltage, multiply it by C to get your current. So nothing wild or crazy there, just a little tedious. This problem is just finding the equivalent inductance and equivalent capacitance of these networks. Nothing particularly difficult about that one. This problem is one of the ones that I like. So let's take a look at this. Okay. So in this particular circuit, we have a voltage source in series with an inductor in series with a capacitor. And we are asked to find the source voltage if we know what the capacitor voltage is. So let's draw this out here. So this is homework number, I don't know what that happened there. 12, problem 3, if I'm not mistaken. Here's Vs of t. Here's some inductance L. Here's some capacitance C. Here's Vc of t. I'm going to make a little note over here. Vc of t is known. Vs of t is what we're trying to solve for. Okay. So because this is a single loop circuit, all of the elements are connected in series. How I would approach this problem is by using Kirchhoff's voltage law. So I am going to define the voltage drop across my inductor with the positive polarity on left, like so. And I'm going to go ahead and define this current I flowing clockwise around this loop. So my source voltage Vs of t is going to be the voltage drop across my inductor plus the voltage drop across my capacitor. Okay. The voltage drop across my inductor recall from Thursday's lecture, is L times the derivative of our current. So L di by dt plus Vc of t. But we don't know what the current is. That being said, because we know the capacitor voltage, we should be able to figure out what the current flowing through the network is, right? So as a quick aside thing here, we know that I that's flowing around this loop will be C times the derivative of our capacitor voltage based on the first relationship that we introduced today. So if I substitute that in, I find that my source voltage is LC times the second derivative of my capacitor voltage with respect to time plus my capacitor voltage. So all I've done to get this relationship for this particular circuit is use Kirchhoff's voltage law to give me an equation to figure out what's going on around the loop. And then I've simply used the capacitor and inductor relationships that were introduced over these last two class meetings. Okay? Nothing particularly hard or difficult about the analysis It's just understanding, hey, if I need current and I know the voltage drop across a capacitor, I need to use the derivative-based relationship. And then the next problem, we're going to wind up using the integral-based relationship. We'll see here in a second. Okay. So let's look at problem 4. Actually, this is a graph problem similar to what you see in the in-class assignment and stuff like that. Nothing real wild or crazy here. Let's look at problem 5. I think this is what I'm thinking of. Yeah. So in this problem, we have a voltage source connected to a capacitance, an equivalent capacitance, connected in parallel to an inductance. So let's take a look at this guy. Right? So here is VS. Here's my equivalent capacitance. I'm just going to call this C for the sake of argument. Here's my inductance L. Let's look here at what's given to us. So we are given IS at 0, and we're given VS. So this is IS of T. We're given IS at 0, and we're given VS of T. And our goal is to find IS of T for T greater than 0. So because this is a single node pair circuit where all of the elements are connected in parallel, I'm going to use Kirchhoff's current law as my starting point here. So I'm going to express my capacitor current IC of T as the current flowing down. And I'm going to express my inductor current IL of T as the current flowing down, so that I can say IS will be equal to IC plus IL. Since I know the voltage drop across my capacitor, I can say that IC is simply C times the derivative of the voltage drop. IL is going to be 1 over L times the integral from T naught to T of Vs of T prime dt prime plus IL at some point in time T naught. Okay. So in 2 simple steps here, Kirchhoff's current law and then using our relationships, I have really gotten down to the crux of this problem because I've expressed pretty much everything in terms of known quantities. The only thing that I have left to figure out is how to get this term IL at T naught. So we're given IS at 0 here. So I could say that, do this at 40. IS at 0 is going to be equal IC at 0 plus IL at 0. Well, rearranging this, I could say that IL at 0, my stylus will write, is equal to IS at 0 minus IC at 0, where IC at 0 is just C times the derivative of the voltage with respect to time evaluated at T is equal to 0. We already had to figure out what IC as a function of time was up here anyway, so we're not really having to do any extra work. So using these relationships, we can simply plug things into our original Kirchhoff's current law expression and solve for this IS of T quantity that we were looking for. Okay. The reason why I like these two problems so much is because, one, they take things back to basics. In my opinion, you guys, once you learn nodal and mesh analysis, you try to apply it to literally everything, regardless of whether or not it's actually the most efficient choice. Problems like these bring things back to the basics of Kirchhoff's voltage law and Kirchhoff's current law, which are what nodal and mesh are based on. And if you can understand how to apply KCL and KVL correctly, you can get a long way in a lot of problems, even if you're not particularly good at nodal or mesh just yet. Okay. Another reason that I like these particular problems is because they make you think about all of the different ways that these quantities are related to each other. Okay. Which is going to reinforce you learning the four relationships for capacitors and the four relationships for inductors. So I don't know how more plainly to put it other than to say, expect to see problems similar to this on your next test. All right, so I have given you guys some pretty strong hints as to how to solve the two most difficult homework problems of pretty much the entire quarter here. I've also given you some hints and suggestions for a couple of other problems from this particular set. I've gone over the relationships for capacitors, and we have discussed how they combine when you see multiple capacitors in a given circuit. Does anybody have any questions for me?
I do, yes, sir.
What can I help you with?
So I guess starting with problem 3, at the end we have the L times C times the second derivative, that part. Yes, sir. So that bottom part there, is that just definition, right? Like, should I just remember that definition, or will it kind of come out in the wash in different ways with different problems?
It'll come out in different ways for different problems. For this specific problem, this is the second order differential equation that effectively governs this circuit, but we don't really have to look at it as a differential equation or anything here. We're just exploring the mathematical relationships, right? So I wouldn't expect you to memorize this, but this relationship is fundamental, and this relationship is fundamental, meaning that I would expect you to have those two memorized.
Okay. So I guess how did you get to the second derivative? Am I overthinking it?
So all I'm doing is I'm taking this relationship right here and I'm plugging it in for I of T.
Okay, okay.
So I took the derivative of this relationship, which is where I get the second derivative from.
Okay. Okay, yeah, that's fair. Okay, I see it. Yeah,
Okay.
the two D's multiply together. I mean, like, you know, like kind of
Well,
basic.
so let me do it a bit more explicitly here. So the derivative of I of t with respect to time is going to be the derivative with respect to time of c dvc by dt, right? C is a constant, so we can take that out. So the derivative of the voltage is the second derivative of the voltage.
Yeah, okay.
Oops, make that menu go away. Yeah. And then we just have to multiply through by that L.
Okay.